Welcome all of you. In the last one or two classes, we discussed a lot about polarization transfer. What is a polarization transfer? How we can enhance the signal intensity by taking the signal from the magnetization from abundant spin like proton and give it to the dilute spin like carbon 13. And conceptually we can visualize this by selective population inversion or selective polarization saturation of a particular transition. This is what we saw that, and especially in the case of heteronuclei, and the signal enhancement goes by the ratio of the gamma. We also saw that, and then of course when we understood how the polarization transfer takes place vectorially with the vectorial drawing, we understood how the components of the doublet of this proton coupled carbon, how it was changing as a function of delay, as a function of different pulses when we apply. And it was antiphase character, how we made it to refocus and became in-phase character, so that there won't be nullification in the intensity or reduction in the intensity, so that we can immediately after collecting the signal we can do the decoupling also. So we we understood lots of tricks and tidbits of how we can get the polarization transfer. And of course insensitive nuclear enhancement of polarization transfer, which is called the inept, is a common thing which is always used in all the two-dimensional experiment, especially heteronuclear two-dimensional experiment like HSQC, HMPC, etc., where the polarization transfer is very, very important to enhance the signal intensity. And of course in the one-dimensional way we can also use it for identification of different carbons by spectral editing, depending upon the delay that we are going to give in the last delta delay in the inept sequence. Then we know that we can identify carbon, CH3 carbon, CH2 carbon, CH3 carbon based on their intensity and then phase of the signal, whether it is positive or negative. Similarly, we saw the depth sequence. Depth sequence also is similar to this inept. At the last pulse we are going to have a different flip angle pulse, 45 degree and 190 and 135 depth sequences. Again we can use this. It is a polarization transfer technique again, but we can also use this to identify different carbons. We can use this for carbon 13 editing. These are all one-dimensional experiments. We can, of course, depth is not combined with 2D very often, but inept is combined. So we will come to that when we come to 2D later. With this we will now jump over to a different topic. This is called, so far we discussed about coherence transfer, everything in the inept. We will discuss more about these things now. I am going to touch upon what is called the coherence transfer pathway today. Coherence transfer pathway. What is a coherence transfer pathway? We will see that. The equilibrium magnetization, it is along z axis. Is it coherent? Coherence means all the spin vectors should be in phase. It is not there. They are not coherent. Every spin is preceding with a random phase. As a consequence, the z magnetization, the equilibrium magnetization is not coherent. Whereas if you consider apply a pi by 2 pulse and bring the z magnetization to xy plane, then what is going to happen? All the spins are instantaneously have phase coherence. Immediately they have a phase coherence. After some time they start undergoing decoherence. That is what we discuss when we discuss about the T1 and other things, especially FID decay, we discuss that. So after a certain time what will happen? The spins will completely lose coherence and become completely dephased. So immediately after 90 degree pulse, there is an instantaneous phase coherence, and then phase coherence get destroyed, completely destroyed with time, and spins will come completely dephased. So that means pi by 2 pulse generates coherent system, and decoherence takes place is a different question, but we can say pi by 2 pulse generates a coherent system. Once we know that, we can also define what is called a coherent order. That is something new term which will tell you, we will discuss. And P is a term which is generally used, always used, to refer the number of quanta involved in the generation of coherence. The coherence can be, it depends upon the number of quanta. It is P is equal to 1 means single quantum, that is coherence of coherence order 1. P is equal to 2 is coherence order 2. Depends upon the order. We can define upon the quantum of the coherence, we can define coherent order. Okay. Now consider a single spin off nucleus. It has two states. that we all know, spin of nuclei alpha and beta states. Now delta is equal to delta m, this is of course minus of, this is plus of. Now delta m is equal to plus 1, it is the transition from alpha to beta. The change in spin angular momentum is from alpha to beta, that is plus of minus of is plus 1, that is delta m equal to plus 1, the transition from alpha to beta. Similarly, delta m is equal to minus 1 is the transition from beta to alpha. These are called single quantum coherences. That is what we discussed long back. When I come to MQT multiple quantum, I will discuss this. And these are called coherent orders 1 and 2, I am sorry, plus 1 and minus 1. Remember, these are single quantum coherence, and I call this as coherent order 1 and 2. Plus 1 is the coherent order this one, and minus 1 is the coherent order this one. So the transition from alpha to beta is called coherent order plus 1. Transition from beta to alpha is coherent order minus 1. This is important. Remember what is a coherence order. Now, if we consider also start with the Z magnetization, which is in thermal equilibrium. This is not coherent, but we still call coherent order 0. There is no coherence order for that. The Z magnetization is not coherent, it is undergoing, all nuclear spins are undergoing precision with different frequencies, different phases are there. So single quantum coherences have coherent orders either plus 1 or minus 1. Remember, Z magnetization is coherent order 0, single quantum coherences are coherent order plus 1 or 0, minus 1. Similarly, extend the logic, double quantum coherences are coherent order plus 2, minus 2. Like that you can have generate different coherent orders depending upon the spin system you are dealing with. Okay. Now, if I want to select a particular coherent order, I want to detect, let us say, only minus 1 coherent order signal. Is it possible to do that? There is a way to do that. That is what is called coherence pathway. If I know how the signal is going, how the this coherence is getting transferred from one path to other path, if I know this way it is going, I can choose the proper coherence pathway to acquire the signal of my particular interaction. If I want to get a particular interaction to detect signal for that interaction, if I want to choose a particular pathway for that, we can do that if I know the coherence pathway. So phase cycling is one thing which eliminates all the artifacts that can appear in the NMR spectrum, and we can do that by using what is called phase cycling. That is why I introduced about pulse phase and receiver phase earlier. The basic requirement to define a coherent order for each spin system is that is a requirement. It is, we have to define a coherent order for each spin. Then we can also define the overall coherence order for an operator product. These two things are important actually. Okay. Now we will go to the important concept. These are all tidbits. These are the points you have to remember, and then we use these things in understanding coherence transfer pathway. The free precision, for example, delay. You apply a radio frequency pulse and give some delay, and then apply another pulse, no problem. During this delay, we discussed a lot about chemical shift evolution, J coupling evolution, etc. Fine. But this free precision will not change the coherence order. That will not change during free precision. Only RF pulses which you apply, that can change the coherence order. Okay. So a 90-degree pulse on equilibrium magnetization creates only plus 1 and minus 1. Now with this logic, now we can apply, there is a equilibrium magnetization along Z axis. You are going to apply a 90-degree pulse here and then bring the magnetization to other axis. Then you are going to create plus 1 and minus 1 coherent orders. 90-degree pulse always from thermal equilibrium, if you apply 90-degree pulse, it creates plus 1 and minus 1 coherent order. We already discussed what is plus 1 and minus 1. Plus 1 is transition from alpha to beta, and minus 1 is transition from beta to alpha. So beauty is we can select a particular transition pathway. Okay. So for coherence pathway, particular coherence pathway we can select. Now by convention, P is equal to minus 1 is what is the coherence which is associated with plus omega naught, and P is equal to minus 1, and P is equal to plus 1 is associated with minus omega naught. That is because the sense of precision, and we always use nu is equal to minus gamma into b naught over 2 pi. This gamma is coming into the minus is coming into the picture. That's why this is a simple thing. You don't worry. But please remember p1 and p minus 1 are they are depending upon the omega plus omega and minus omega. And important concepts. 180-degree pulse changes the sign of the coherence order. If I have a coherence order plus 1 in a particular path, I apply a 180 pulse immediately after that, this will change the path to minus 1. 180 pulse will change the sign of the coherent order. Plus p will become minus p. Let us I have chosen a coherent order 2. Apply a 180 pulse. Immediately I will go to coherence order minus 2. And p equal to minus 1 is always detected in the spectrometer. All spectrometers are designed in such a way you cannot detect p is equal to plus 1. You detect only p is equal to minus 1. That is the coherent that pathway is always chosen. And pulses on the XY magnetization creates higher quantum orders. This is the important point. Remember, when I have a thermal equilibrium magnetization, you apply 90-degree pulse, bring to XY plane, you create plus 1 and minus 1 coherent orders. That means you are already in the XY plane. Now you apply another pulse, some more pulses, 1 or 2 or 3, whatever you want. Then what you do, if you apply the pulses on the XY magnetization, you create higher quantum orders. Like plus 1 minus 1 become plus 2, 3 plus 3, 4. You can go to higher and higher quantum orders. That is possible. For that, the magnetization must be in the XY plane. XY magnetization must be there. You can't create that from the Z magnetization. Similarly, for n coupled spin system, the maximum coherent order that you can create is plus n or minus n. If I have 3 coupled spin system, maximum coherent order is plus 3 and or minus 3. If I have 10 coherent order, they have 5 coupled spin system, maximum is plus 5 and minus 5. This is the important concept you have to remember. Now consider a situation we have 2 spins. How many coherent orders we can think of? See, we can have coherent, we see this transition is allowed, okay, and this transition is allowed. This is single quantum, this is single quantum, this is single quantum. So these are all correspond to p plus or minus 1. This is also allowed, double quantum. 2 spins simultaneously flipping from alpha beta to alpha or alpha to beta. Simultaneously flipping. This is order p plus minus 2. Going from here to here is plus 2. Coming from here to here is minus 2. Similarly, p plus minus 1. There are 4 possibilities. Here to here, from you going from here to here, alpha going to beta is plus 1. Here beta coming to alpha is minus 1. So there are 4 such single quantum. You have 4 such plus p and plus 1 minus 1. But plus 2 and minus 2 is only 1 plus 2 and minus 2. Similarly, you can think of transition from here to here. See, I will show you here. See, now you can think of transition from this state to this state. Okay, that is alpha to alpha beta to beta alpha. That is 0 to 0. This is 0 quantum. This is p is equal to 0. Then you may get confused. I told you the Z magnetization order is 0, coherent order is 0. But you say this also is coherent order 0. Don't worry, there is a way to distinguish that. Both are 0, I agree. But if you have to detect only this 0 quantum transition, we can do some trick. Okay. But now, how the coherences evolve at different stages of pulse sequences? This is a way we can understand by doing what is called coherence transfer pathway. CTP it is called. Using this coherence transfer pathway drawing, I can understand how the coherences are evolving at different stages of pulse sequence. Now let us look at this one, how we do. The pathway always starts with equilibrium. We have to start with, if you start with somewhere else, already magnetization in the XY plane, you have created higher quantum order, but you do not know where to start. You always start with, equilibrium magnetization, that is p is equal to 0. You have start with p is equal to 0 quantum order, and then first pulse, as I told you, always create plus minus 1. Then subsequent pulses will create higher quantum coherent orders. The last pulse always should create p equal to minus 1 order, because I told you only p is equal to minus 1 coherent order is going to be detected by the spectrometer. Any other coherent order will be rejected, you cannot detect it. So, whatever you do between the pulses, start with 0 in the thermal equilibrium, apply 90 pulse, create +1 and -1 coherent orders, and in between you do many pulses. Finally, you have to choose the coherent pathway in such a way the last pulse should create only p equal to -1, then only we can detect the signal. That is the important point. Now, 90 pulse other than the first pulse always generates higher quantum coherence. That is what I told you. Other than the first pulse, 90 pulse, first one generates higher quantum. First one you apply 90 pulse, first time it creates +1 -1. Apart from that, any pulse you apply, second 90, third 90 pulse, they create only other higher quantum order. Only this one create single quantum order. Okay. Now, how this coherence evolve, you can write by a coherence transfer pathway diagram. That is what I have been telling you. Now, how do you write that? First, let us take a simple example for a pi/2 pulse. What does a pi/2 pulse do? You know that the magnetization is along x axis, it will bring into xy plane. If I apply a pulse, magnetization along z axis, you apply x pulse here and bring the magnetization to y axis. That is what you are doing. For a pi/2 pulse, simply it will bring the equilibrium magnetization from z to transverse plane. That is all it does. Now, let us write a diagram for that. How do we write a diagram? It is very important to know how you write a diagram for the this coherence transfer pathway. Okay. So, now I am starting with a 90-degree pulse, and initially the magnetization is along z axis in thermal equilibrium. So, this is what a 0 quantum order or 0 coherent order, p is equal to 0. Now, I am applying a RF pulse. When I am applying an RF pulse, what is going to happen? It will create two coherent orders like this. Now, we brought the magnetization to the xy plane by applying a 90 pulse. Now, this was p is equal to 0 we started with when the magnetization was along z axis. Now, as soon as I apply 90 pulse, you have created two more coherent orders, +1 and -1. This 0 is always there. 0 is there, but in addition to that 0, you have created +1 and -1. Two coherent orders you created just by application of a 90 pulse. So, simply what we did is to write the coherent diagram is very simple. What we have to do is, I wrote a pulse here. Before that, the magnetization is along z axis, and then it is a p is equal to 0 state, 0 coherent order, and then apply 90-degree pulse, bring the magnetization to xy plane. Now, you have already created p is equal to +1 and p is equal to -1 path order, it is here. So, now this to this is called a pathway from 0 to +1. Okay, when the magnetization in the xy plane, we have generated two coherence pathway. From 0, we created a pathway 0 to +1, and we created a pathway from 0 to -1. These are the two coherent pathways we have created just by application of a 90 pulse. That is why I said 90 pulse create p is equal to +1 and p is equal to -1. What does a 180 pulse does? I told you also when I gave the tidbits. 180 pulse inverts the populations. That means it also inverts the coherence order. We can see that. Now, this is a 90 pulse. Already I told you, after I apply 90 pulse, we have created coherence order plus p is equal to +1 and p is equal to -1. Initially it was 0 along z axis. During the delay, of course, nothing happens, I told you. Delays, free precision will not change the coherence order, it remains same. During the delay, +1 and -1 remains same. Now, you are applying 180 pulse, double this width. 180 pulse interchanges the coherent order. This +1 comes to -1, -1 goes to +1. Now, you have interchange here after the 180 pulse. This is the important concept of 180 pulse. 180 pulse inverts the coherence order. And finally, what is the change in the delta p now? If I go from here to here, From minus 1 I went to plus 1. What do you mean by that? Because of 180 pulse I change the coherent order from minus 1 to plus 1. The difference is 2. Minus 1 to plus 1. Minus 1 to minus 1, plus 1. You have to say this is P1 and this is P2. Okay. So, we should always P2 minus P1 minus P2. You take it. Now, this is the initial stage minus 1 and P2 is plus 1 minus of plus this to minus 1, it is minus 2. You have changed the quantity, this delta P. If you go from here to here, it is minus 2. If you come from other to here, it is plus 2. Either way is possible. You can select from here to here, that is also possible. Plus 1 to this thing also you can do, or you can select from minus 1 to plus 1 also, both are possible. But the change is 2, it could be minus. Now, we can say final change is minus 2, I am telling you, depending upon what I am choosing. So, P2 to P1, P2 minus P1 is the final state, P2 is the final state and P1 is the initial state. What is the final state for me? If I consider here to here, final state is plus 1 and initial state is minus 1. Okay. Plus 1 minus of minus 1 is equal to plus 2. If you go from here to here, delta P is equal to plus 2. If you come here to here, plus 1, here to here, minus 1 minus of plus 1 is equal to minus 1. Here, if you go from here to here, it is minus 2. If you come from here to here, it is plus 2. Okay. Let me make it clear for you. Okay. Now, P2 minus P1 is what you have to consider. See, P2 minus P1, P2 is the final state and P1 is the initial state. So, now which is our final state and which is our initial state? Let us say I go from minus 1 to plus. Minus 1 is my initial state. Initial state is P2. No, this is wrong, I made a mistake here. P2 is the final state, this must be P1. So, P1 is a initial state, that is minus 1. P2 is the final state is plus 1. So, now I have to consider P2 minus P1, plus 1 minus of minus 1, which is equal to 2. So, if you go from minus 1 to plus 1, change delta P is equal to plus 2. If I come from here to here, initial is plus 1, minus of minus 1 is equal to 2. Okay. So, depending upon which one is your P1 and which is your P2, you can find out what is delta P. Okay. This point you have to understand. As you go ahead, we can find out more of these things. How to design the sequence of phases? One can select or detect a certain component of the coherent order. It is possible. If the pulse changes the coherence from starting state P1 to the desired state P2, let us say I start with minus 1 and then I want to take it to plus 2, let us say some state starting with minus 1 to plus 2. It is possible. Now, this is the initial state, that is P1, and this is the final state. Starting state is P1, final state is P2. If the phase of the pulse is phi and the phase of the chosen pathway of the receiver is this one. See, if you want to select a pathway, you should know what should be the receiver phase. Okay. What is the receiver phase? The receiver phase is given by simple equation minus of delta P star of 5. 5 is your phase. Okay. What is the phase of the pulse you are applying? That is the pulse phase. 5 is your pulse phase. Now, minus delta P is what is the change of the pathway from initial state to final state. If you know this, simply you have to set the receiver phase, which is calculated by minus P delta P into 5. Then you can automatically select the particular coherence pathway. For example, in the previous example, 0, this is the minus 1, plus 1 is there. If I got to go from here to here, minus 1 to plus 1, minus 1 of the initial state, minus of plus 1, which is equal to minus 2. So, now delta P is equal to minus 2. If delta P is equal to minus 2, you put it here. Okay. So, my delta minus of minus 2 into 5. So, it is 2 times 5. If my receiver phase is, let us say 90, transmitter has to be 180. You can have a sequence of pulses, sequence of receiver phase pulses. I can change the pulse of the receiver, let us say 90, 180, 270, 360 like that. Correspondingly, receiver phase has to be doubled like this. Then you can select the particular pathway here, +2 pathway. You get the point how to choose the pathway. So, that is the simple equation. You should not forget this equation. This equation is going to tell you the receiver phase is equal to minus delta p into phi. Phi is nothing but a pulse phase. See, phi is a pulse phase and this is the receiver phase, and you have to remember the equation. Delta p is the change in the coherence pathway from initial to final stage. If you know that, then you can work out this thing pulses are receiver phases and the pulse phases for any sequence of your choice, and you can select any particular pathway of your choice. Now let us see in the CTP for a one pulse experiment. What is a one pulse experiment? One pulse experiment is simply apply a 90-degree pulse and start collecting the signal. What does the 90-degree pulse will do? I told you the 90-degree pulse creates +1 and -1 quantum coherence orders. +1 coherence order and -1 coherence order is created. Now I want to select only this one, -1. What is my delta p? Initial state is 0. Okay, P1 is equal to 0. What is my P2? P2 is equal to -1. What is delta p? Delta p is always P2 minus P1. P2 is -1 minus 0, it is -1. So delta p is -1. Delta p is always final phase minus the initial phase. That is what you should find, which is the path, final path minus the initial path, that you have to remember. So delta p in this case is -1. We started with -1. I started with 0, we wanted to get -1. So P1 is equal to 0, P2 is equal to -1, delta p is equal to -1. So now what should be my receiver phase? Minus of -1, because the equation is receiver phase is minus of delta p into phi. What is delta p here? Delta p is -1. So minus of -1 into phi. Minus of -1 is, so it is just phi. So whatever may the pulse you apply, whatever may be the pulse phase is phi. That is a transmitter phase or pulse phase, whatever you call. The pulse phase, if it is phi, receiver phase also has to be phi. Then you can select only this -1 delta p equal to -1 pathway. In a one pulse experiment, if you want to select delta p equal to -1 pathway, you have to have a pulse phase which is 90, then receiver phase is 90. If the pulse phase is 180, if you increase the phases of the pulses, then this also correspondingly increase 270, 270 and 360 and 360. So this is how you are going to do that. So if the phase of the pulse is phi, we need the receiver pulse also same phase. Okay. This is the table which is going to tell you. Look at, I am doing the experiment acquiring 4 scans, and each time I am changing the pulse phase, I am changing the transmitter phase. First I will use 0, the receiver also has to be 0, because that is what I calculate, minus delta p into phi, which is only just plus phi. So it is same, if this is 0, this is 0, this is 90, this is 90. So if I use this pulse phase and receiver phase, then what is going to happen? You will select only particular pathway, that is -1. This also has an advantage. I am moving the receiver, I am moving the pulse in different axes from plus x, y, minus x, minus y. Accordingly, receiver also is moved. So every time we are coding the data, and if there is any imperfections, that will be removed. And this is a phase cycling called cyclops. Cyclops is a phase cycling, is a 4 pulse cycle in which transmitter phase and receiver phase is identical. The transmitter phase is 0, that is pulse phase, receiver phase is also 0, and you move the pulse phase in each acquisition by 90 degree. Start with plus x, go to y, minus x and plus y. Correspondingly, you have to move the receiver also simultaneously along with the transmitter pulse, in which case any pulse, any imperfections which are there, that can be removed. And this sequence is a phase cycling called cyclops. Okay. Now how does it work? We will see diagrammatically. Start with let us say first you have a receiver phase here and you have brought the magnetization here. Magnetization is here and receiver is here. Now I will move this to by 90 degree. I will take the pulse to minus y axis, receiver is also here. I will take it to minus x axis, I put the receiver also at minus x. Now I will take to plus y, I will put the receiver also, receiver is plus y, our pulse also at plus y. What is happening? You see, receiver is following the transmitter pulse. You know, if the receiver pulse is along x axis, receiver is also kept along x. So now for minus y, it is here. For minus x, receiver is here. Similarly, and all the 4 acquisitions, every time I change the pulse phase by 90 degree, each time I am moving the receiver also by 90 degree along with the pulse phase, along with the transmitter phase. Then what is going to happen is phase of all the pulses and the receiver are incremented by the same amount. So signal will add up by the same sign. In case if there is any imperfection, that get eliminated. So if the pulse phase is constant, supposing you may ask me a question, yes, I was trying to do an experiment, identical experiment Cyclops, where the pulse phase and receiver phase both are identical for all the 4 scans. Keep incrementing pulse phase, identically increment the receiver phase. It is very simple sequence. Now you do change the pulse sequence, pulse phase by 90 degree, x equal first x, then minus x, minus y, plus y, all those things. So you are changing the phase of the pulse by 90 degree, but let us say you forgot to increment the phase of the receiver. What is going to happen? We will see this by simple drawing. Now let us say this is pulse is along x, receiver is here. Now what I can do, another thing, your pulse is here and receiver is here. Your pulse is here and the receiver is here. Your pulse is here and the receiver is here. So what is happening here is you are changing the receiver, but pulse phase you are not changing. You are forgetting to change the pulse. Then what will happen? But of course we understood what is positive absorption, what is negative absorption, what is positive dispersion, what is negative dispersion and positive dispersive signal, everything. Now in the same logic, if you have a signal here, okay, if magnetization is here and if a receiver is here, then you are going to get dispersive signal, positive dispersive. Here is negative dispersive here. Here you get negative absorptive, positive absorptive. Now you are going to add up the signal. What is going to happen? This and this will nullify, this and this will nullify. The coaddition of this thing results in complete cancellation of the signal. That is very bad. So that is what is going to happen. So if the phase cycling has to be properly chosen. You know find out the delta P, what you want. You know what is the pulse phase. First define your pulse phase. That is your choice. You can have 90, 0, 180, 270, whatever it is. Once you know that, once you know delta phi, use that receiver phase as a minus delta phi into plus into phi. Find out what should be the receiver phase. Accordingly keep changing with that along with the pulse phase. Then you will choose the right pathway you want, and any other thing we discard, completely removed, it will be discarded. Or if you make any mistake, you get nullify the signal. So we will further understand. Now the time is up. We will see what will happen if I have to select a different pathway, or if I select one pathway, will it not will the other pathway not get revealed, will not get through along with that. Can I reject a particular pathway, or when I select one particular pathway, whether all other pathways are rejected or not? These things we need to understand. We will do that later. So in this class, this thing what we discussed today, we discussed about coherent transfer pathway. Some tidbits I told you. For a 90 degree plus pulse, if you apply 90 degree pulse along Z for the magnetization along Z axis, is a plus x pulse or minus x pulse, the plus y or minus y does not matter. You will bring the magnetization to xy axis. You are creating coherent orders plus 1 and minus 1. Coherent order plus 1 is transition from plus alpha state to beta state, plus half to minus half. And coherent order minus 1 is transition from minus half to plus half, that is beta to alpha. And the first pulse always creates coherent orders plus 1 and minus 1 from the equilibrium magnetization which is in thermal equilibrium. and for that one it is coherent order is 0. For the magnetization which is in thermal equilibrium, coherent order is 0. And once the magnetization in the XY plane, any pulse you apply will create higher quantum orders. And we know how to define a particular pathway. And once you know the pulse phase, I can calculate what should be my receiver phase for a particular pathway which I want to choose. I took the example of a single one pulse experiment where one pulse create +1 and -1 path, coherent orders. If I want to select a -1 pathway, I showed if my pulse sequence is 0, if pulse phases are 0, 90, 180, 270, exactly receiver phase also has to be 0, 90, 180, 270. Then what is going to happen is I can quad the data without any way this thing problems, and all any imperfection, if there are any, they get eliminated. And this sequence is called cyclops. So if you don't do it proper, if there is a mistake, I also showed you can nullify the signal. So these things do happen. So we understand more about the phase cycling and how do you choose the correct pathway, etc. in the next class. So I am going to stop it today. Thank you.